The video for the chapter 6 study guide. This is taken from the little chapter test in your textbook right after the chapter review. One thing, if you look at the chapter review pages, they specify when you need to use absolute values. So if ever you have the root and the exponent match, whenever it's an odd root, you just put x. When it's an even root, you put absolute value of x. And if you remember what we talked about absolute value functions resulting from like inverse functions, that can help. But just in general, this is when that happens. So if you have x squared and you square root it, you get absolute value of x, and that has a lot to do with the inverse of the function of x squared and how it only graphs the top half basically. Or if you have like fourth root of x to the fourth, the answer to that would be absolute value of x. But if you do the cubic root of x to the third, that would just be x. So just in general, this is why that rule works that way, which you'll see in other parts of your textbook. So we'll start with number 1 here. That rule is not going to end up applying here, but we're going to take the square root here. Actually, it will for the x, but I'm going to write this out separately. I'm going to take care of the reduced radical part first, and then I'm going to take care of the x part. Now, notice since I'm dealing with a second root, we don't see a 2, but the 2's, it's obviously a square root when there's nothing there, so I'm going to write the 2 just to help remind me. And I'm going to separate this x cubed into an x squared and an x. And then the y to the fifth, same thing. I'm going to separate it into a y to the fourth because I'm separating into parts that are divisible by 2. And then tack on a y. And if it helps, if you want to put like a little y to the first here, that's why it's y to the fifth. You can do that, but it's really unnecessary to do that. Just like it's not necessary to put it here. I'm not going to put it in the final answer. But you reduce this radical, square root of 54, whichever way you prefer. I prefer to use either the little factor tree thing, or if you can recognize perfect squares, take 54. 54 is 9 times 6. So square root of 54 is square root of 9 times square root of 6. And since square root of 9 is 3, you get a 3 on the outside, and the square root of 6 is still inside. So there's going to be a 3 and a square root. And the reason why I'm putting so much space here is because I know something with my x and my y I'm going to write between those. So now I'm going to look at my x's. If you take 3 and divide it by 2, you get 1 remainder 1. So 1x makes it out. And another way to see that is the x squared, square root, it gives you an x. So you can look at it that way instead. So you can look at it as if you square root x squared, you get x. But if you look at this rule right here, since it's an even root and the power and the root, the index right there, match, you got to use absolute values. And then for the y's, all right, 4 divided by 2 is 2, or you could see it as 5 divided by 2 is 2 remainder 1, so 2 y's make it outside. This y here is stuck inside, so just like this x is stuck inside. So this is the final answer that you get. 3 times the absolute value of y squared times the square root of 6xy. That's the answer for number 1. For this next one, we have the cube root. And this one, I encourage you, just do this in your calculator. I'll do it first without a calculator. I happen to know that the cube root of 27 is 3, so there will be a 3 involved. And notice how I have 3 decimal places moved over. So I can put, and the cube root of a negative you can do, it is a negative. So for that reason, you get negative 0.3. But I'm not going to have a lot on there that are just purely just the numbers. But if you do ever have one that's just numbers, please, or just the number part, feel free to put it in your calculator. So you can go to the cube root again by hitting math and option 4, and you can enter this, enter it in exactly like you see it, and it just spits out the answer. An alternative way to do that, instead of cube rooting, is that you can raise that to the 1/3 power. It's usually what I prefer to do, and notice you get the same answer. So either way, you get negative 3/10 as your answer. For the third one, we're taking the fifth root of something. Again, I like to kind of separate everything out You might get nervous that there's a negative under a radical, but it's an odd root, so it's going to work out. I'm going to separate this out. And even if you only do this mentally, I really find the separation is helpful, so that's not overwhelming. But you don't have to write all this out. This, I'm going to do this time instead of using a perfect, doing it in my head. I'm going to actually prime factor it to let you practice that way. Take 64 and I'm going to factor tree this thing. And you can do it various different ways, but just keep picking factors of the number that's on top until you end up with prime numbers as the final result. So like, I could have, instead of going 8 and 8, I could have done 32 times 2 or 16 times 4. But either way, you're going to get the same prime factorization. You get 6 2's either way you do it. So an interesting way of seeing this is 2 to the 6th power instead of writing out all the 2's. So notice how it works just like variables. If you take the exponent, divide it by the index, and so I get 6 divided by 5 is 1 remainder 1. So that means there's 1, 2 on the outside, and then there's 1, 2 remaining on the inside. And let me not neglect my negative. And it's just good practice that, we're taking in. And since we want to simplify the radical, it makes, more sense to pull the negative out of the odd radical. Common mistake for me is I forget the index, so I'm just going to remember to write that 5 every time. But another way you could have seen this is, okay, I can write the 6 2's, and the index says you need 5 to break out. So 1, 2, 3, 4, 5 2's gives you 1, 2 on the outside, and then so notice there's a 2 stuck on the inside. So either use the exponential trick that we have to use with variables, or you can, use a little breakout method, whatever way works for you. For this one, I could write out, 14 x's, but I'm just going to use the division trick. Take 14. If I divide it by 5, I get 5 goes into this twice, and you get a remainder of 4. So that means 2 x's make it outside of the 5th root, but 4 x's are stuck inside. 2 x's make it out, and then 4 x's are stuck in. Okay? And then for this last one, 20 divides evenly by 5, so this is just going to be y to the 4th. And there, you don't need absolute values at all. First of all, because you're dealing with an odd root, and second of all, because the exponent and the root don't match each other, so there's no reason to worry about absolute values there. This is your final answer, but I kind of want to clean it up. I want to put all the radical parts together. So first, I like to put the constants. I like to put the variables that are outside in alphabetical order. It wouldn't be wrong to put y fourth first. So I wouldn't take points off, but it would just kind of bother me, and I would probably make a note on there. So it's just nice to put in alphabetical order. Try not to make this. This is a 5th index. This isn't attached to that y fourth. It's attached to the radical. So write it close to the radical. And then we have 2 that's in the root, x fourth that's in the root, and none of the y's are in the root. So this is your answer right here. And if you want, you can clean up. I can erase that little part right there. And that's the answer for number 3. In the next section, we're performing operations, either adding, subtracting, multiplying, dividing on radical expressions. So we're going to multiply the 7 and the 14. That's one option. So if you take 14 times, you're going to get 98, but then you have to take that 98 radical and reduce it. So, and you can do it like we did earlier with the 64 and like prime factor it, but let me show you a trick I prefer. Since we're multiplying these radicals, okay, just like we can separate the radicals if that's convenient, we can combine them too. So this is 7. Well, what is 14? 14 is 7 times 2. And notice how we have 2 7s? So a 7 breaks out. That's a lot easier to me than having to take 98 and prime factor it and all that, because it's just a big number. So, but you can confirm that if you take the square root of 98, that is the same thing. Even though we don't want to write it in decimal form, we want to leave these in radical form. That's the same thing as 7 times square root of 2. So if you're ever not sure about how to reduce radicals, you can use your calculator to help you like guess and check. So I just find that convenient. And then we have the x part. So we got 3 x's, but then we got one more x, so don't forget there's an invisible 1 right here. So that means that's like an x to the fourth here. And since we have a square root, the square root of x to the fourth is x squared. So that we have the 7 that made it out the radical, but also 2 x's make it out the radical. And then the only thing stuck inside is the 2, which is stuck inside the square root. That's your answer for number 4. For this one, we have a radical in the bottom. So I want to start by rationalizing this denominator. So whatever radical part is in the bottom, if you multiply it by its own radical, what it does is it outputs that object but without radical at all. But that's not fair to just do something to the denominator, so let's do it to the numerator as well. And this, there's understood parentheses here, so you have to actually distribute this root of 6x to each part. So yeah, we rationalize the denominator, but now we got to rewrite the numerator. So we're not changing this expression. So 1 times square root of 6x is just 6x. And then this part right here is, this is square root of 6 times 3, and then there's an x times an x. So again, I could have written 18x squared, but I prefer to leave it in factored form. I find it more convenient. So this is correct, except we could simplify this right here. This is square root of 18, but you could write it this way. You could view this 6 as 2 times 3, so the 6 is 2 times 3. And then there's that other 3 that was already there. And then there's the x and the x. So instead of writing it as a big number, you can write it out in factored form. And notice that a 3 breaks out and an x breaks out. And remember that the denominator is still 6x. So if you rewrite this thing with this radical simplified, we get square root of 6x minus, there's a square root, but the 3 makes it out. The x makes it out. The 2 stuck inside. And all of this is over 6x. And just a reminder, even if you're tempted, do not think that you can like cancel out this 6 with this 6 right here. This is a radical, this is not. And even though there's a 3 and a 6 here, don't do this. Okay, this is bad. Don't go, oh, reduce this, so that's a 1, that's a 2, and that's a 2. That is not okay to do. Specifically, if this 6 were outside of a radical, then it would be okay to do all that because this 3 is not in a radical, that 6 not in a radical. But this one's in a radical. You can't reduce something in a radical with something not in a radical. So our final answer is just this, and that's as reduced as it gets. Here we're adding radical expressions. It might seem like you can't do anything here, but before you do anything, try to reduce the radicals we have here. Square root of 48. If you reduce 48, you can prime factor it. So we have 8 times 6. 8 is 2 times 4. 6 is 2 times 3. And then the 4's break down further. This is a square root, so I see a pair of 2's, another pair of 2's. So that means 2 2's make it out. And then the only thing left is square root of 3. So this is actually 4 square root of 3. With 27, 27 is 3 3's. Or you could see it as it's 9 times 3. So either way you see it, that's a 3 on the square root of 3, which don't forget that this 2 is here. So 2 times 3 is 6, so that's 6 square root of 3. And you'll notice, hey, now we can combine these. 4 and 6, 4 potatoes plus 6 potatoes makes 10 potatoes. And then I bet this 12 is also going to be reduced into a square root of 3. Boy, that would be convenient. Well, 12 is 4 times 3. All right, 4 is 2 times 2. Hey, look, that's 2 square root of 3. Don't forget that 5 is here. So 5 times 2 is 10. Let me rewrite. So that's consistent with the rest. So that's 10 square root of 3. So 4 plus 6 is 10, plus another 10 is 20. So you get 20 square root of 3 as your answer. For this, we have two binomial radical expressions, and the multiplication is implied. So a lot of people, like to say FOIL. You could use that method. So all we're doing is really just distributive property. So multiply those out however you. So here I color coded, the distributive property that I'm working with, And this is them unsimplified, and I have the the signs, like some of these are negative. And then you just simplify them. Notice how we have radicals here. You can multiply radicals. So I could get square root of 20 times 5 is 100, which reduces to 10. Or you could have individually reduced these if you wanted as well. But either way, this simplifies right here to a 3. Okay, 3 squared of 20, nothing happens there. 3 squared of 20, but square root of 20 can be reduced. 20 is 4 times 5, and 4 is 2 times 2. So this is really 3 times 2 square root of 5. So that's 6 square root of 5. Even though it looked like I couldn't do anything with that, 20 could be reduced. And then that's plus, very little happens here. That's just 2 square root of 5. Oh, but look, now these can be combined in the middle where it looks as they couldn't before. Minus, and then this is 2 times, since 5 times 20 is 100 and square root of 100 is 10. This is really 2 times 10. So that means this is minus 20. The 20 can combine with the 3, and it's a negative 20, so we get negative 17 out in front. A negative 6 combined with a positive 2 is a negative 4. So you get negative 7 minus 4 times the square root of 5. For number 8, I notice that the radicals are exactly the same already. So 4 potatoes plus 2 potatoes is just 6 potatoes. So we just get 6 on the square root of 7xz. Remember that we never combine, like you're not going to get for your radical 14x squared, z squared, or anything like that. Because we don't do it for anything else. If you take 4 centimeters and you add 2 centimeters, you get 6 centimeters. And that's it. So this is, just think of this, 4 units plus 2 units gives you 6 units. For this next one, we want to rationalize the denominator. We have to multiply. It's a little more complicated when you have a binomial. You don't just multiply by the radical part. Since there's 2 radical parts, and it's separated as a binomial, because it's separated by a plus or minus, you have to multiply by the conjugate of that the denominator there. So this part right here, we know that we can do the little shortcut method. You can do the long FOIL way, but square root of 7 times square root of 7 is 7. And then we know the middle parts will cancel out. Root 7 times this, root 2. But then we have negative root 2 times root 7. We know those will cancel out. So I'm going to fast forward to root 2 times root 2. So that's square root of 2 times square root of 2 is 2. So this is our new denominator. And then the top part we just distribute. 5 square root of 2 times square root of 7 is 5 square root of 14. And then 5 square root of 2 times another square root of 2 is going to be 5 times 2. So we get 5 root 14 plus 10, if you simplify 5 times 2. All of that is over 5. And some people prefer to write like the 10 in front. That's an option. I'll probably do that first. But this time, all the things divisible by 5 are outside of radicals. So we can reduce all those. That reduces to 1. That reduces to 1. That reduces. So we actually have a denominator of 1, so there's no reason to write the denominator. But you have 1 times square root of 14, which is just square root of 14, plus 2. Or you could write it as 2 plus square root of 14. I prefer this way, but this way is also true. Notice how there's no variables here. Now, even though we're dealing with a pretty big number, if you have just a number with no variables, don't be afraid. Just like on an ACT test, you can do it without a calculator. And on at least half of the SAT tests, you're allowed to use your calculator. Now, what if the answer is like multiple choice and they don't have this decimal as a choice? Well, hit math, enter, enter. All right, you could have done this by hand also. This is the answer. The answer is 0.04 or 1/25. We usually prefer fractions. But here's a way if you like to know how to do it by hand. A negative exponent is the same thing as a reciprocal. So it's 1 over 125 to the negative 2/3. Oh, but to the positive 2/3, because once you flip it, you don't have to write the negative anymore. A the third thing is really a root. So that's 1 over the cube root of 125. The 2 is an exponent. So if you cube root 125, you get 5. If you square 5, you get 25. So that's why the answer comes out to 1/25, doing it by hand. For number 11, we can simplify these by using the rule that when you multiply powers with the same base, you add the exponents. So you take x and you raise it to the power of whatever 1/6 plus 1/3 is. And off on the side, the common denominator is 6. So it's really 1/6 plus 2/6, so which gives you 3 over 6, which gives you 1/2. So your answer is x to the 1/2 power. If you're sloppy at adding fractions, remember you can add them in your calculator by just using the division sign as, sort of like a fraction operator. You can also use alpha y equals, but this is quicker. 0.5, if you want to convert that to a fraction, math and enter, that's 2 ways. And even though I could also write this as square root of x, because the original problem started in exponential form, I'm leaving the answer in exponential. Here, there's 2 ways we can do this. We can either simplify what's inside first and then raise it to this power, or we can distribute the power to everything in here. Now, because there's so much stuff in there, I'm going to go the route of simplifying first. So 8 and 27, well, there's no common factor between that, so I'm just going to write 8 on top, 27 on the bottom. But as far as the x's, there's 9 on top and 2 on the bottom. So 2 will cancel out. You'll be left with 7 on the bottom. Or you can use the subtraction rule. When you're dividing powers, you subtract the exponents. Whereas the y's have more on the bottom than the top. So the y's have 9 more because 3 cancel out. And then now I'm going to worry about that power because I don't have to deal with as much stuff. Well, what is a 2/3 power? Well, 2/3 power is you're squaring each thing, but then you're also cube rooting it. So if it helps, this is the cube root of all this stuff raised to the second. So I can write the 2 first, or you can see the second power as written, like you can do that after. So either way you do it is fine. You could square the 8 and you get 64, right? Then you cube root 64 and you get 4. Guess what else I could have done? You could cube root 8 and get 2, and then square that and you still get 4. So either way, either direction you do it, since exponents and radicals, they're the same thing. Radicals are exponents. So in the order of operations, they happen at the same time or whatever order you want. I can square 27 and get some huge number and cube root it, or let me just cube root 27 and get 3. And then 3 squared is 9, so we got a 9 down here. And when you're dealing with exponents, remember you don't directly, I'm not going to cube root the number 7. When you're dealing with powers, you're going to kind of divide 7 by 3 and then, here multiply it by 2. So that's a little shortcut rule. So off on the side, I know I have x to the 14th because 7 times 2 is 14, and that's going to be cube rooted. Here I have y to the 9th squared, so that's going to be y to the 18th, and then that's going to be cube rooted. And I'm going to use my little division rule. So how many sets of 3x's can I pull out of 14 x's? So off on the side, I'm going to do 14 divided by 3. And similarly, I'm going to have 18 divided by 3 here. So 14 divided by 3 is 4. It goes in 4 times with a remainder of 2. So that means 4 x's make it out, but 2 x's remain inside. 2 x's remain inside the cube root. And then for the y part, 18 divided by 3 is 6. So there's just a y to the 6 that makes it. So this becomes our final answer. Okay, for 13, it looks like I can't combine these, but I haven't given it a shot yet because I haven't tried to reduce it. So let's try to reduce 8. 8 is 4 times 2, and I can break that 4 down into 2 more 2's. But either way, you get 2 square root of 2. And then x to the 5th, but we're square rooting it. You'll notice 2 x's make it out, and 1 x is stuck inside. So the radical part reduces to just square root of 2x. I would sure hope, since the first one reduced to just a radical with a 2 and an x inside, I bet the second one will reduce that same way. 18 is 9 times 2, and we notice that the x's behave the same way. So I know that the x's are going to pull out the same way. So you got x squared on the outside, and then you got the x is stuck inside, just like in similarly the 2 is stuck inside. Square root of 9 is 3, so it happens to work out. So we get 2x squared times something minus 3x squared times something. So off on the side, what is 2x squared? I'm going to subtract these sort of like coefficient terms in a way. These are like terms, 2x squared minus 3x squared. Whatever that is, times the square root of 2x. So we get negative x squared times the square root of 2x as our final answer. Okay, this will be the last stuff we'll do in the first part of the video. We're solving equations, like radical equations, not just simplifying expressions. So we're going to do it 2 ways, one by hand and then one using the calculator. So if you do it by hand, remember the step 1 is to isolate the radical. It's already isolated. Square both sides of the equation to cancel out the radical, or it doesn't have to be square. I mean, it could be cube, but it's a square root in this instance, so I'm going to square it. And so it drops what's in the radical, it drops the radicand out. And then this you have to FOIL. Don't just write x squared plus 25 here. That would be a mistake. It's x squared minus 10x plus 25. If you FOIL that, you'll get the same thing. Now that we have this, we have a quadratic. Well, that presents a problem because to solve a quadratic, you can't get x by itself. You have to get it in standard form. So I'm going to move this x over because you got to get 0 on one side. I'm also going to add the 3 to each side. So you end up getting 0 equals x squared minus 11x plus 28. Now at this point you have 2 options. You can put this in your calculator and find the zeros, the x-intercepts. You could also try to factor it by hand. And actually, there's more than you could guess and check it. There's actually several options. You could also use quadratic formula. So whatever one is your favorite. This one I happen to be able to recognize that it is factorable. You know, x, my favorite factors of 28 are 7 and 4. And it just so happens that -7 and -4 add up to 11. So the solutions, I think, are x equals 7 and x equals 4. If you want to use quadratic formula, you can do it by hand, of course. But in my calculator, and you will hopefully have this in your calculator too, you can run the quadratic formula program. If you want to do it by hand, there's the formula that we programmed in. But I'm just going to enter these values. 1, the b is -11, the c is 28, and we should get the same answer, 7 and 4. Now, the instructions said check for extraneous solutions. So they say the answers are 7 and 4, but let's see if both of these really are solutions. If I plug in the 7 in place of the x, and it gives me the same thing on both sides, then that means it's solution. So this is square root of 4. The square root of 4 is 2. That checks out. 7 minus 5 is also 2. Okay, so 7 is definitely a solution. Well, what about 4? Let's look at x equals 4. Let's do square. So square root of 4 minus 3 is square root of 1. The square root of 1 is 1. Okay, so the left side is 1. But 4 minus 5 is -1. Guess what? This is sort of like a false solution. So your solutions are not x equals 7 and x equals 4. It's just x equals 7. Another way you could do this, and I think this is the most efficient way in this case, but you could also look, and you can even use just to check your solution. You can put into each side of two equations in your calculator, each side of the original equation, put 1 in y1, put 1 in y2. And if you graph these in the standard window, usually you'll see them intersect. And notice how they only intersect at one place. They intersect at what appears to be x equals 7. If you want to get a clearer picture on that, you can do second, calc. The intersect option is option 5. And when I try to go to the first curve, it doesn't like, 0 is not in the domain, so you have to actually go a little over to the right. See, I'm still not on the first curve. So that's the drawback of using your calculator. So I hit enter, I'm on the first curve. Now I'm on the second curve, hit enter a third time. Look at that, the intersection is at the x value 7. So in my opinion, calculators, it takes longer to get the answer there, but it is still possible to find the solution that way. But just remember that even though you get two solutions, because squaring both sides of an equation it's only semi-legal, sometimes you get fake solutions. So solving them using a calculator is always an alternate option. And to show your work, you can just describe the buttons you hit. But I'm going to do most of these solving by hand. So for 15, I'm trying to get x by itself. I'm going to square both sides, which remember is sort of semi-illegal. It's kind of legal, but it's kind of not. And so conveniently, I get two linear solutions. So this could be, I'm not have to use quadratic formula at all. So you just get 4 equals 2x. Now I'm going to divide both sides by 2. So you get x is equal, 4 divided by 2 is 2. X equals 2. Still check your answer. If I put a 2 here, I get square root of 6. If I put a 2 here, I get square root of 6. So either way, you get square root of 6 equals square root of 6. So 2 is going to check out for 15. For number 16, okay, this is technically a radical right here, so I'm going to rewrite this so we can kind of apply those rules. Remember, our fourth root, is also a 4 in the denominator, so that's x minus 1. And then this is, you can see this two ways if you want. You can either put the third power on the inside or on the outside. So this is a one way to rewrite the left side of the equation, and that's optional to do that if you want. I'm going to look at that. I'm going to look at that another way. If you want to leave it in that exponential form, you know that you want to get x by itself. So before we even worry about any roots, get rid of this 2 that's not included inside of this root. So if you divide by 2 on both sides, you're going to get x minus 1 to the power of 3/4 is equal to, this is just 8. And you can individually get rid of these. If I want to get rid of a third power, you cube root both sides. So it's like that's how you can get rid of that third power right there. If you want to get rid of the fourth power, you raise to the fourth both sides. But it's a lot easier to see, I believe, when it's in radical form like this. So the reason I'm cube rooting here is to get rid of this third power, or see the third power there. So you end up getting this cancels out with this. So you get x minus 1, which is now just to the 1/4 power, or it's fourth rooted, is equal to the cube root of 8, which is 2. Then to get rid of this fourth root, we fourth power both sides of the equation. So you end up getting the radicand part broken out. So you get x minus 1 is equal to 2 to the fourth is 16. Okay, and now just add 1 on both sides. So you get x is equal to just 17. You should check your answer. And this time I'm going to check it instead of by hand. I'm going to check my answer on the calculator. Let me just make sure that if I plug exactly what I see, replacing the x with a 17, let's see if it outputs a 16, because the right side doesn't have to be simplified. So check your answer always. 2 open parentheses 17 minus 1. Raise that to the 3/4 power. Since I get 16, I know that that's a valid answer. For our 17, I'd like to start by squaring both sides, but guess what? The radical is not by itself. If you started squaring both sides, you'd get a big mess right here. So first, remember to like move anything that's not part of the radical over before you start squaring. So then I square both sides. The radicand here drops out. And then I'm going to FOIL this side. That's x squared plus 2x plus 1. I'm going to be dealing with another quadratic. Move these over to the other side because to solve a quadratic, you got to get it in standard. And once you get to this point, you can factor it by hand. I don't love factoring always. Sometimes I'm a little sloppy at it, but I'm going to try to, because I'm dealing with prime numbers, like 2, the only one to get a 2 is 2 times 1. And then, all right, I get try a positive 2 here and a negative 1 here. So I think my solutions are x equals 1, but also x equals negative 2. Now, it might be true that both these solutions work, but maybe only one of them works. So you should check it. If you replace x with 1, if this statement is true, then that means 1's a solution. So this is square root of 4 minus 1 equals 1. 2 minus 1 equals 1. 1 equals 1 checks out. Let's try putting a negative 2 into here. If I replace the x's with a negative 2, I get square root of 1 minus 1 equals negative 2. Well, square root of 1 is 1. 1 minus 1 is 0. 0 is not equal to negative 2, so this is an extraneous solution. It's like a false solution. So your only solution is actually x equal 1. Again, you can also use graphing to help you check or confirm, or you can just run this in your graphing. Like in the home screen of your calculator, you could do the check part there. But since both sides had a variable, that's why I decided this time to, um, you replace it out because I don't want to have to think of the x in my variable or the x. Just reminding myself that this gets substituted in with the value, so I did it by hand. But that's it for part 1 of the video. And again, this is mostly focusing on radicals, simplifying them, combining them, and solving radical expressions and equations.